Hello everyone, my name is Julin. I'm a senior computer science student from the University of Pittsburgh. As part of Carnegie Mellon's Robotics Institute Summer Scholar Program, I conducted research on automated content editing in NeRFs, or neural radiance fields. Before I discuss the main contributions of our work, I'll first provide a brief introduction to neural radiance fields and their important role in neural rendering. It is difficult for computers to understand the 3D world. If you look at these pictures below, our world is composed of a nearly limitless collection of shapes, colors, textures at varying depths. All of these factors further complicate a computer's ability to understand the surrounding 3D world. Neural radiance fields, or NeRF, bridges this gap between our complicated world and a computer's understanding. NeRF is a relatively new development in the computer vision community, only being published in 2020. It is capable of constructing a 3D representation of a scene given a sparse set of 2D images. It accomplishes this task by representing a static scene as a fully connected deep network with a 5D coordinate input x, y, z, theta, and phi, and an output of color and density, RGB, and sigma. The figure below outlines this method in further detail. In part A, we see that given an image from a given viewing direction theta and phi, we will pass a ray through each pixel. As that ray is sent through the pixel at location x and y, a sampled point z is sent through a fully connected deep network and is outputted a color and density, where density is a value that denotes whether or not an object is present. This process of sampling a point along the ray and passing it through the deep network to receive an output of color and density is repeated for every sample along the ray as shown in part B of the figure. Whenever this process is completed, we can now combine all of the points that were sampled using a classical volume rendering technique and receive the final prediction of the pixel's color as shown in part C. The final step of the NeRF method is to compute the loss between the rendered color for the pixels and the ground truth, and take that loss to reduce the rendering error in future iterations. We directly applied this method to our own images. In part A of this figure, we captured roughly 150 images of our scene using a moving camera to have good viewing direction coverage. After the images were captured, they were passed through a tool known as ColMap to obtain the camera position or viewing direction of a given image with respect to the scene. This is important because without the poses, there is no structural information of where these images were captured in relation to other images, which is essential for 3D representation. With the images processed and poses obtained, we directly used NeRF's method of sending rays through each pixel, sampling along the rays, and rendering the pixel color for all of our images. The final rendered output, along with its depth map, after 200,000 iterations, can be seen in part C. From only 150 images, this 3D representation was pretty impressive. But what if we wanted to manipulate or edit these neural radiance fields? How might we do that? It turns out that this is not an easy task, and is the subject of much of the recent NeRF research. We found that one of the most effective and simplest ways to make edits to neural radiance fields was to do it at ray level, meaning that we entirely remove the rays that pass through pixels that we wish to edit. Doing this effectively makes it such that those removed rays are not rendered whatsoever. To remove entire objects from a scene and remove a large number of rays, we utilize binary masks where the area marked as white would be removed and the areas marked as black would be unaffected. When comparing figure C with the object removed to the standard rendering B, we see that this method was a clear success. The object was fully removed from the scene. Moreover, when we invert the mask and the originally white pixels become black and the black ones become white, we can fully remove the background of the scene while preserving the object as shown in figure D. While this method did yield impressive results, there is a significant problem of scalability. Each of the binary masks that we need for each of the approximately 150 training images is obtained through manual annotation. This process is extremely tedious and becomes even more apparent with an increase in training images that need annotations. One solution that we found was to utilize an automatic annotation software known as BodyPix 2.0. As shown in the video below, the segmentation software works quite well. It is both quick and accurate. The only downside of this tool is that it only works at segmenting humans. This will certainly be the subject of our future research. Using this tool to create binary masks was another clear success. When comparing Part B to Part D in the figure below, the person is almost entirely removed from the scene, and we can see directly behind it. The shoes of the person are not fully removed, but this can be attributed to imperfect masking. Nevertheless, this result was still surprising. As shown in the initial example of removing the rays, this method also works for removing the background and preserving the person as shown in Part E. Our usage of automatic masking also extends to a dynamic NeRF variant known as CoNeRF. CoNeRF stands for Controllable Neural Radiance Field and is capable of controlling simple dynamic movement within a scene through the use of, up until now, manual masking of the controllable component and an assigned value for its transitions. As shown in Part A of the figure below, we first captured a large number of images containing simple dynamic movement, such as lowering and raising of the arm, and assigned a value to each image, with a value of -1 meaning that the movement is in its start state, a value of 0 meaning that it is in its halfway state, and a value of 1 meaning that it is in its final transition state. All the other values from -1 to 0 and 0 to 1 are assigned to the appropriate frames that capture those transitions. Next, we pass these images through our automatic annotation tool, BodyPix 2.0, and obtain accurate masks of the dynamic component, which in this case is the arm. Using both the assigned values and generated binary masks, we get a controllable output. Our future steps for this project are to expand with different types of segmentation software, apply this method to scenes with multiple maskable objects, improve the masking coverage, increase the editing possibilities, and extend this method's benefits to other NeRF variants that rely on manual annotation. This research was funded by the National Science Foundation. I want to say thank you to the program organizers, Dr. John Julin and Rachel Burson, and my faculty mentor, Dr. Laszlo Jenny. Thank you all for listening to my presentation.